All right. So the problem type we want to solve here, search type. So the three fundamental types, problem types in algorithms: search, sort, and selection. Problem. Okay, 3S. Yeah. So we discussed sort a lot. Selection, we solved it, right? Remember? So although we didn't discuss too much, but the whole problem is solved. Remember, we have a solution, linear solution. So the whole problem is treated as solved. Okay? But the search, we have a lot of things to do. So let's look at how many algorithms we have learned so far for the search problem. Linear search or sequential search, another binary search. Okay, these two big one, pretty, most important. Another, not that big, very small, so we will mention a little bit, index search. Okay, yeah. So now the fourth one, hashing. Okay, all right. So let's look at why we need to have a new search. The basic problem, how to find a data item with a given key. The fundamental problem. Okay. So here, given a collection of data dynamically. So we discuss about dynamic data a lot. Because in the real world, you need to prepare for the data like that, dynamic data. Now, each data item is identified with a unique key. Yeah, data. So how do you identify a data? Typically, we use a unique key. Yeah, so that's the typical property we use. The question: how to make your data search efficiently? So what do you mean this efficiently, right? So we always talk about the efficiency. What do you mean efficiently? All right. So here, let me still go through our current search and algorithms. Linear, what is the efficiency? Big O of n, right? Binary, what is the efficiency? Big O of log n. Index search, big O of 1. Okay? So here you can see. So regarding the efficiency, we need to compare with the efficiencies of the current algorithms. So relative to the current search algorithms. You cannot talk about abstract efficiency. So you need to compare it with our current search algorithms and see which one we should target, which asymptotic class we should target, right? Definitely we don't want to target this one, right? Because the slowest, linear. Okay, yeah. Binary search, pretty good, right? But index, so good, okay? So we would like to set our target as good as this, right? Yeah. Otherwise, if you set a goal binary, we already have the binary search. You just set the same goal. So what's the point, right? But index search, you may argue this, we already have the index search. So what's the point? There is a big problem on index search, the range problem, right? The value of the range cannot be too large. If it's too large, so it is a really bad algorithm. That's why. So this one, on paper, it looks good, but not realistic. Okay? So in the real world, the index search is not very realistic. Okay? So we need to develop a new algorithm with this big of one, but also realistic in the world. Realistic in the world. So you can use it in the real world. Okay? Without any limitation, range, restriction, you can always use it. Right? So that's a big problem to solve. All right. Next, let's look at the data structure. So here, because regarding the efficient search, nobody tells you what data structure to use. In other words, you have freedom to choose your data structure. Okay? So that's good. We can design a new data structure. So we know typically a data structure helps us to organize our data. So here we need to be very creative. So when we create a new data structure, we try to put some nice property in it. Okay. So then we can take advantage of this great property to help us do the efficient search. So that's the basic idea. Okay. All right. And this data structure should also be able to handle dynamic data efficiently. So when the data comes in, all right, so you can easily place it in your data structure efficiently. Okay, yeah. And next time when you do the search, it is also efficient. Okay, right. All right. Now, in order to get a better idea here, I want to do a table to summarize or to compare our current searching algorithms and try to narrow our design in certain direction. Yeah, that's the goal. All right. Properties, algorithms. The algorithms, so far we have these three. Okay. All right. The data structure, for all these three, we use array data structure. So simple, straightforward. Okay. Yeah. So not much to do. Just to grab it and use it. Okay. Efficiency, I just list before, like these three different categories. Yeah. So now you can see we set our target on this one. Okay. Ordering, right? So here, this property, the ordering property, we can consider a little bit ordering. What's that? Unsorted. Linear search, we can apply on unsorted data. Okay? The binary search, you require your data must be sorted. That's a big requirement. Okay? Otherwise, you cannot apply binary search. It's a very restrictive requirement. Index search, unsorted. Yeah, so if you do not require your data sorted, then that means less restriction. So you can apply it on more general situation. Yeah. Dynamic. Okay. So the dynamic data, when the data items keep coming in, how much is the cost you put it into your data structure, satisfying the requirement of your data structure, how high is the cost? So that's why we need to consider that factor. Dynamic data handling maintenance, that cost. Yeah. For linear search, yes, it can handle dynamic data, right? Binary search, very hard. So when a new data item comes in, you need to insert it into a sorted array. In order to make the insertion, complete the insertion operation, you need to do very expensive operations. You need to shift large number of elements to the end. And that operation is very expensive. So that's why we say it's costly. Okay. Yes. So, you can do it easily without high cost. So that's the meaning of yes. So you can handle it well without any hesitation. So that's yes. Yeah. Costly, you need to think about it. Yeah, the cost is too high. It may not be a good idea to use it to handle the dynamic data. That's the meaning. We look at the cost. To give us that idea. All right. Efficient sorting. Yeah. So at the end, we consider, because sometimes we may like to get sorted data, efficient sorting. Linear search, no. Yeah, because the data is not sorted. If you want to print out your data in ascending order, you need to do a lot of work. But binary search, yes. If you want to output your data just from beginning to end, so easy. Yeah. Index search, you cannot. All right. Now, with this table, now you can see what we try to target our new search algorithm and the data structure. Yeah. Our new one, we need to design a new data structure. Yeah. Not necessarily array. So array may not work well. So we need to have some creativity for this step. All right. Our target, bigger of 1. Okay. Close to that of the index search. Close to. We do not try to compete with the index search. But close to. Okay. Yeah. That's good enough. Yeah. Unsorted. Yeah. Because this step, we cannot ask too much. Think about it. If you ask that supporting sorted data, then you ask too much. Then probably nobody can do it. So because this property may not be that critical for our algorithm, so we drop it. We don't require it. Okay. Yes. Yeah. So we, handling dynamic data, that's important. So this one we want to have very low cost. Yeah. And efficient. Yeah. So we don't need this. Yeah. So we try to make design relatively easy. Yeah, otherwise, nobody can do it. Okay, so if you emphasize these two properties, nobody can do it. Yeah. All right. So now you can see there is a similarity between index search and our new search algorithm. Yeah. So that means we should use the index search as our starting point to design this new data structure. Okay, all right. So let's recall the index search. How much we need to modify. We have to modify the structure of the index search. But where do we modify the index search? All right. Generalize the idea of the index search. Okay. So the key point here, the most important point here. Okay. So let's look at the biggest problem of the index search, range problem. The data range could be too large, then it is very hard to use space to manage your data efficiently. That's the biggest problem. Okay? How do you choose your space in an efficient way to arrange your data? So that is the biggest problem in the index search. Okay? Yeah. So here, actually, we are looking at the problem called direct addressing problem. Direct addressing, index, yeah. So the address direct. So you get index. So that's the address of the data. So you go there, you find your data. Direct addressing. That property, for your index search, very big one. Okay, so that's the key property. This key property we can describe in this way. Given the key, that corresponds to index of the entry directly. The key and index of array, 1-to-1 correspondence. No change. No. Directly, right? So that's why we call direct addressing. That property. Okay? Convenient, easy, fast, but not efficient. Yeah. So we want to really improve its efficiency. All right. So the main problem here, when the keys are long, but you only have a small number of elements. That's quite common in the real-world application. So we have long keys. Okay? We cannot use direct addressing because that will use too much space. Okay? Too expensive. Too much space also means too expensive. The cost is too expensive. Okay? Yeah. All right. So the problem is direct addressing would waste a lot of space. Direct addressing problem. So when we move to our new search algorithm, we need to fix this problem. We need to modify this addressing part. All right? Fix this addressing problem. Then we can get a solution. Yeah? So that direction is very clear after this analysis. All right. How to use space efficiently. So our next question is we need to be creative to use space efficiently. All right? Yeah. Here, I may like to show you a simple example. Okay. Yeah. So, in real-world applications, many times we use long keys. Okay. Our data, okay, typically could have long keys. For example, social security number or your student numbers, that's quite long. Right? Yeah. Because so many students, so many people in the world or in the country, so they need to be identified. So the number must be long. But your application only works for a small group of people. So you do not write an application that need to work for all the people in the world or even in this country. You rarely do that, right? So you write an application work on much smaller group of people. Okay, so that's why the number involved in your application usually not very big, the data size here. Okay? For example, the social security number for a student, that's long. Okay? But in a class, let's say we only have 40 students in a class. Okay? Now we want to create a data structure to store 40 students. So you cannot use the long key social security number or student number. Yeah, let's say student number. Yeah, because maybe, yeah, we need to protect, right? Yeah, credential, we don't want to, expose social security number. So let's say the student number. How about that? Yeah. Student number. So definitely for 40 students, you cannot do direct addressing. Okay? Yeah. So you cannot use your student number as indices of an array directly. Not efficient. Okay? So you need a huge array, but only you store 40 students. So that's a really bad idea. Okay? So what is the solution? In order to solve the problem, how to make keys shorter? In order to use it as indices of an array, how do you make those keys shorter? Or the question like, how to map keys to slots? We only have these 40 slots. Okay. How to map those long keys to these 40 slots? That's the question. Okay, we need to answer. All right. Mapping strategy. Now let's talk about the mapping strategy. So here you can see the issue becomes a mapping issue. Mapping long keys into relatively small number of slots. So that's the main problem we need to solve. Okay. All right. So what is a good mapping? When we consider a mapping strategy, we need to have criteria for a good mapping, right? So the guideline. Yeah. So what properties do we have for our mapping consideration? Yeah. All right, so let's look at the criteria. First, fast calculation. When you do mapping, you need to do calculation, right? Because it is not direct addressing. Direct addressing, you do not do any calculation, but that is really bad. But now we do indirect addressing. Okay, we change from direct addressing to indirect addressing. You need to do calculation. But that calculation should be extremely fast. We don't want to waste a lot of time to do calculation. Okay? Yeah. So that's the first criterion. Yeah. Second, evenly distributed among all the slots. This is probably also important. Evenly distribute the mapping locations among all the slots. Okay? If your mapping is really bad, so you map most of the keys in a small number of slots, that will be very bad. The performance will be extremely bad. Okay? So that's why the second property also important. Okay? The third property, another important one, not sensitive to any pattern. So what's that? This one is not easy to see. Not sensitive to any pattern. Because sometimes data could be given in certain pattern. Yep. So it is possible the data given in some kind of pattern. So we don't know. So various patterns, we don't know. Yeah. But your mapping strategy should be very stable, very solid, very reliable. So it still works quite well, even for data with some special pattern, you can still handle that efficiently. So you can see these criteria not very easy to achieve. Okay. So you need to do something smart to get your data structure supporting these 3 criteria. Or large part of the criteria. It may not be 100%. Yeah, so it's hard, but 90, how about 90%, right? 90%. Yeah, so things like that. All right. So implementation. Yeah. With these guidelines, next question is implementation. How do we do that mapping? How do we find a mapping way to have these properties? Okay. So the issue becomes choose appropriate math functions. Because mapping, what's the mapping? A math function. Math function. Okay? So that's a most straightforward connection, relation about the mapping. A math function. Okay. So we call these math functions hash functions. So the issue becomes how to design your hash functions. Okay. All right. So that's our introduction part. Okay. So this introduction explains the background, why we need to do things like this. Okay. All right. So our next part, we will look at the hash function design. All right.